So this is Elec1 2019 question 5. Part A. An ideal op-amp has infinite open loop gain. What is the significance of the term open loop in this context? Well, most op-amps we meet have negative feedback loops, but open loop is where we have a op-amp such as a comparator where there is no feedback loop. So the answer is no feedback loop. And that is from the output to input of the op-amp. Okay, part B, part 1. An op-amp is used as a comparator, monitoring the output of a light sensor. When the light level falls too far, the comparator output switches to positive saturation to turn on the lamp. Part of the circuit is shown in the next diagram. For part 1, complete the circuit diagram by adding the light sensing unit made from an LDR and another component. Well, the first thing we need to ascertain is this a light sensing or a dark sensing circuit? Well, we're told that when the light level falls too far, the comparator output switches to positive saturation. And we know that resistor and LDR needs to be attached to the non-inverting input. Well, what this means is that it must be a dark sensing circuit. And if it's a dark sensing circuit, then the resistor needs to be above the LDR. So we're going to have our LDR at the bottom, our resistor at the top. Let's just give that R. And the attachment to the non-inverting input is going to be in the middle. Okay, B part 2. At what value of input voltage, Vin, does the lamp turn on? Now, we're given no resistor values for the LDR or the resistor, but what we are told are the two resistor values, that this is 100k and the bottom resistor attached to the inverting input is 200k. So what we can do is we can use ratios, and we can use an equation which is the voltage, and in this example it's going to be Vin, is going to be the resistance of the bottom resistor value divided by the total resistance, and then multiply it by the voltage of the supply. And this gives us an answer of 8 volts. Part 3. In this situation, what is the advantage of using an op-amp with a very high input impedance? Well, we need to know what high input impedance means. And high input impedance or high impedance means high resistance. Now, what does that mean in terms of a circuit? Well, high impedance normally means small current. And that is the advantage of using the op-amp, that only a small current will be pulled by the op-amp from the sensing circuit. So a small current is used by the op-amp consequently not impacting the sensor circuit. Okay, part C. Okay, so part C, we have an ADC. So the circuit diagram shows a simple flash ADC. The logic system is used as the priority encoder. Now, a priority encoder basically decodes the output from an ADC into binary. And we can see on the right-hand side that we've got a binary output for B and A, and we've got a other output which is P, but we might come back to that. It says the analog signal is set to 60 millivolts. Which op-amp outputs will be in positive saturation. Now, the way we figure this is by working out the voltages up the ladder. Now we've got 100 millivolts for Vref, which means that we have 25 millivolts on top of the first resistor, and then 50 millivolts on top of the second resistor, and 75 millivolts on top of the third resistor. Now what does this mean? Well, it means that for our analog input, if it's 60 millivolts, then the non-inverting inputs of op-amp Z and op-amp Y will both be in positive saturation, because 60 millivolts exceeds both the 25 millivolts for the inverting input of Z and the 50 millivolts of the inverting input in Y, but doesn't exceed the 75 millivolts of the inverting input of X. So when it says which op-amps will be in positive saturation, the answer is Y and Z. Okay, so for the next question, what is the resulting binary output BA? Well, we have two of our op-amps, Y and Z, with positive saturated outputs, which means that we're looking for the binary value of 2 at B and A, and 2 would be 1, 0 in binary. Part 3, what is the advantage of this type of ADC over the digital ramp ADC? The most significant advantage of a flash ADC over a digital ramp ADC is speed, and so the advantage is that the flash ADC is faster. Okay, D part 1. A microcontroller is configured to have a 9-bit input port. An 8-bit ADC is connected to the input port of the microcontroller. How many op-amps would the modified circuit need to include overload indication? And that is where output P comes in. So output P has its own op-amp, and we need to bear that in mind. Normally for an op-amp, for an ADC, the number of op-amps is given by 2 to the n minus 1, where n, because that's the small n, is the number of bits. So what we're looking at is 2 to the 8 minus 1. But because we've got an overflow indicator as well, which is output P with its own op-amp, we've got plus 1. So really, we're just looking at 2 to the power of 8, which is 256 op-amps. Okay, so part 2. What is the resolution of the ADC? Well, resolution is the reference voltage divided by the number of op-amps. So resolution equals Vref over N. So we're looking at 100 millivolts, or 100 times 10 to the minus 3 over 256, and that gives us a value for the resolution of 3.9 times 10 to the minus 4 volts. The only caveat I would give with that is this only works when all the resistors in the ladder are the same. Okay, if they're not the same, then you need to use the smallest resistor value in order to work out the resolution. Okay, that concludes question 5.